Okay, so the first topic today, আমাদের যেটা, that is the Hertzsprung Russell diagram. Okay, so the Hertzsprung Russell diagram, a Hertzsprung and Russell এরা দুইজন সায়েন্টিস্ট, অ্যাস্ট্রোফিজিসিস্ট, তারা দুইজন মিলে এই ডায়াগ্রামটা বানাইছে। Left, the diagram that you see in the left, it was produced by Hertzsprung and Russell by observing different stars on the galaxy, by looking up at the stars by using telescopes. Okay, from data from the other from data from like the Hubble Space Telescope and other telescopes, they produced this diagram. Okay, now understand this, that although this looks like only a few dots in this diagram, there looks like only a few dots in in this diagram. The actual diagram has like lots and lots of more dots. Okay, now if I show you that diagram, then it will be very confusing and you won't understand it well enough. So our focus is to understand the diagram rather than to see the actual diagram. If you want to see the actual diagram looks kind of like this. Let me show you. The actual diagram looks kind of like this. Yeah, this is from Wikipedia. Okay, so like this is the actual diagram, what kind of looks like. But the thing is, in this diagram you can see there are lots of balls, right? So those points are blobs. Those blobs, each of them are a star. Okay, anyway, so let me explain from this diagram what the hell is the Hertzsprung Russell diagram. So what is this Hertzsprung Russell diagram? So I will start writing here some bullet points regarding this diagram. Okay, so first thing is the first point. Oh, damn it. Yeah. Okay, this. Sorry about that. Okay, so yeah, the first point is that this is the Hertzsprung Russell diagram. It's called the Hert. Oh wow, I forget the spelling. It's a very weird spelling. So yeah. So the Hertzsprung Russell diagram. Okay, the Hertzsprung Russell diagram. It is also called HR diagram. Now, what's the speciality of this diagram? The speciality of this diagram is that the axes are logarithmic. Okay, I don't know why this is not working. Um, yeah, finally it works. Okay, so the Hertzsprung Russell diagram, or HR diagram in short. So what this diagram is, that first of all, what you need to notice is that the axes are logarithmic. I'll explain what this means. The axes are logarithmic. Also, it's a plot of, why is everything bold? Yeah. So, and why is the font so weird? Yeah. Okay, cool. It's a plot of all the stars that have been discovered so far. Okay, so any star that we discover, we put that star on this diagram as a plot. So you see Proyokon B is a star, Sirius B a star, Barnard star, Proxima Centauri, the sun, Hey, that's a familiar star. We know this guy. Right up there in the sky, yeah. The sun. And then Altair. Altair actually sounds like a Assassin's Creed character, but anyway, this is also on the name of a star. Sirius. Sounds like Sirius Black, a Harry Potter character, but yeah, this is also a star. Regulus, Akemar, Aralaire, Aldebaran, Mira, Antares, Betelgeuse, Canopus. So yeah, lots of weird names by given by lots of weird people, lots of weird astrophysicists. Whoever discovers a star, he gets to name it. Okay, he or she gets to name the star. Whoever discovers the star, he or she gets to name it, and then that star is put somewhere in this diagram. Now, where is the star, or where a star will be put in a diagram depends on a lot of things. Okay, first of all, the axes are logarithmic. Okay, so and then the x-axis. The x-axis can be two things. Axis is just plural of axis. Okay, so axis na axis. Okay, axis is just plural of axis. Acha, axis mane ki y axis, x axis, right? That's axis. Okay, so y axis, x axis. So y axis, x axis are usually in a graph, but here something is odd. A lot of things are odd here, so that is why there is not. It's not the same. It's we're not calling it a graph because its axes are weird. Okay, its axes are weird. That is why we are not calling it a graph. We are calling it a diagram. The axes are logarithmic. What do I mean by logarithmic? What do I mean by the word logarithmic here? Okay, so you see the in a normal graph, you will see. I don't have a normal graph here, but if you know a normal graph, I'll just quickly bring a graph picture. I'll just quickly bring a picture. Okay, so like this is enough. Yeah, I'll just quickly bring it up here. Okay, so you see this is a okay. This is a very bad resolution photo. I need a better one. Yeah, I think I can copy this. Paste it here. Why is this happening? Yay! Hello. Okay, finally, yeah. You see, this is how a normal. Uh, hey guys, please focus on the topic material. This is gonna be very interesting. Today's class will be very interesting. Focus on the topic material. Okay. So you see, this is how the axis on a normal graph paper looks like. So on a normal graph paper, you will see the gap between 0 and 5 and the gap between 5 and 10 are equal, right? Because 5 units, 5 units. Also the gap between 10 and 15 and the gap between 5 and 10 are equal because 5 units, 5 units. But look at this. Look at this. Um, if this is 0 and this is 4000, so this gap is 4000 and then a larger gap, but this is only 2000. 4000 minus 6000, this is only 2000. And then see this is 1000, 6000 and 7000. This gap is 1000, but the next gap is 3000. See, so like this gap is 1000 but this gap is 3000, so it's very, like, I don't know, like you understand what I'm saying. The gap between 1000 and 3000, 1000 and 3000 should not be the same gap, right? This is 5, this is 5, but when you say minus 5 and minus 15, the gap is 10, and this gap is actually twice as large as this gap. But that's not the case here. The gap between 7000 and 10,000 is 3000, but এইটুক যতটুক 6000 7000 এর গ্যাপটাও অতটুক, so this doesn't make sense. Also the gap between 10,000 and 30,000, it's not, it's weird, right? Yeah, so that's what I'm saying is a logarithmic scale. This is called, the axes are logarithmic. Okay, so logarithmic means the values do not increase linearly, they increase logarithmically. Okay, so 4000, 6000, and then rapidly 7, 10, 30. Okay, 4, 6, 7, 10, 30. Now you have to remember these values. That's the weird part. Okay, so like I will kind of like let me get rid of this. We don't need this anymore. Um, Let me just bring up some. Do I not have pencil here? Insert. Drawing. No. Okay. Never mind. I'll just bring up something like, yeah, circle. Yeah. Okay. So like you need to remember. Oh. Okay. I didn't want that. Not fail. Yeah. You have to remember these values. Okay. This value is very important. Okay. You need to remember this 4000 Kelvin value, and also you need to remember. Let me just make it a little more visible to you. Yeah, so you need to remember this value of 4000, and you need to remember this value of 30,000. Okay, so you need to remember these two values, 4000 and 30,000. What are these values? Kelvin temperature. Kelvin temperature. Okay, so the on the x-axis of the Hertzsprung-Russel diagram, on the left you have 4000 Kelvin, on the right you have 30,000 Kelvin. So again, this is something weird. The x-axis increases in the left direction. Okay, the x-axis actually increases in the left direction. Alright, fine. Cool so far? Great. I mean the x-axis values. Okay, the x-axis values increase in the left direction. Okay, so that's another weird thing about this graph. And you need to remember these two values, 4000 Kelvin, 30,000 Kelvin. Okay, let me make this 30,000 Kelvin is usually blue, so let me make this blue. Yeah, okay, that's cool. Now, what else do you need to remember? The x-axis is not always temperature. The x-axis can be one of three things. The x-axis can either be temperature or color or spectral class. Okay, so the x-axis will be one of these three things. Either it will be temperature. Yes, this is not a normal graph. I'm telling you again and again, this is not a normal graph. That is why we are calling it a diagram. It's not a graph, it's a diagram. So the x-axis will be either temperature or color or spectral class. Here we are showing both. X-axis of temperature, and at the bottom, at the top you can see an x-axis of temperature, and at the bottom you can see a x-axis of spectral class. And actually there is another x-axis that is not written, but there is another x-axis that is not written directly, but it is implied in this diagram. That is the color. You see, on the right you have red, and on the left you have blue, and you see this slow gradual transition. Do you guys remember this transition? You should remember it from this table. You should remember it from this table. Red at the bottom to all the way up to blue at the top. So blue is the highest temperature, red is the lowest temperature. Okay, and in between you have orange, yellow, white, and blue, white. Okay, now if you again go back to this, you see red here, then orange, yellow, white, blue, white, and then finally blue. So on the left temperature increases, so the color goes from red to blue on the left, and also the spectral class. If you think about the spectral class, remember, oh be a fine girl, kill me, oh be a fine girl, kill me. So yeah, the spectral class goes from M to O on the left. Okay, so spectral class also goes from M to O. So if I write all of this, temperature goes from what? 4000 Kelvin to 30,000. Oh, sorry, my bad. Oh my god, what is happening? 30,000 Kelvin. The temperature goes from 4000 Kelvin to 30,000 Kelvin. The color goes from red to all the way to blue, and you have to remember the sequence. And the spectral class goes from M to O, right? If I write the sequence, it's red, orange, yellow, white, and then finally blue. Okay, and if I write this one, you should remember this one. O be a fine girl, kill me. But in this case, it's basically O be a fine girl, kill me is right to left and M to O. So like M K G F A B O. Sorry, O. Yeah, O. Okay. Yeah. I hope you can see this. So these are very important. Okay. Now, how do you remember all of this? You remember all of this by this diagram. Remember it all by this diagram. 4000, you see about 3700 to 4000, all about 4000 to about 30,000. O be a fine girl, kill me. And like red, orange, yellow, you just remember this image. You remember this image somehow. Just look at it for 5 seconds, you will remember it. Yeah. Okay, now back to where we were. So that's that. Fine. Let me just make the font a little bit more. Yeah. Now let's talk about the y-axis. Now you're gonna get even crazier. The y-axis can be one of two things. Y-axis can be absolute magnitude. Remember, absolute magnitude, not relative magnitude. Absolute magnitude, or the y-axis can be luminosity. But the luminosity is a special type of luminosity. It's called luminosity. Oh, I spelled luminosity wrong. Okay, cool. Thank you. Luminosity compared to sun. Okay, and this goes from 10 to the minus 4 to 10 to the plus 5. Okay, so this is very important to remember. Okay, remember what everything that I'm writing on this right side of the diagram, you have to totally memorize this. Okay, you have to totally memorize this. You have to keep them in your head for the exam. Now, absolute magnitude, well, this one's gonna be weird. It goes from about 14 to 0 to minus 10. I should also include here to 1 to that. Yeah. Uh, can I just okay, just yeah, cool. All right, so luminosity compared to sun goes from 10 to the power minus 4 to 1 to 10 to the power 5, and the absolute magnitude goes from 14 to 0 all the way up to -10. And you see I say up to, and because indeed, so as you go from, so as you go, I don't have to write as you go. So from left to right, what happens? Temperature of star increases. On the Hertzsprung diagram, from left to right, temperature of star increases. And from bottom to top, brightness of star increases. Okay, from bottom to top, brightness of star increases. From left to right, temperature of star increases. Clear? This needs to be very clear to you. Okay, so from left to right, temperature star increases 4000 to 30,000 Kelvin, and from bottom to top, brightness increases. Now, if you do not remember the scale of absolute magnitude, if you have forgotten the scale of absolute magnitude, then you will forget, then you will not understand why this is the case. How is the brightness increasing? Remember, absolute magnitude scale is an inverted scale. The more negative, the more bright. The more positive, the less bright. Zero is like somewhere in the middle. Okay? Alright. Now, among all of this, where is the sun? Well, this is another very important. The sun is at a temperature of about, I forget the value. It was, I think, what was the surface temperature of the sun? I told you guys in the previous class, I think. It's about 5,700. Okay, so it's about 6,000. 6,000 Kelvin. So the sun is at a temperature of about 6,000 Kelvin. So somewhere around here, near 6,000, a little bit below 6,000, a little bit below 6,000, the sun, you'll find the sun. And luminosity compared to sun of 1. 1, exactly 1. Okay, so you may ask, why is this? Let me just show you this. Uh, okay, this has not been easy on my part. Um, yep, this is what I was trying to show you. Alright, you see the sun? You see where the sun is? The sun is at exactly luminosity compared to sun of 1, and somewhere around here, which is about a little bit below 6,000 Kelvin temperature, and a little bit before G0, that is, the sun is a G2 star. Okay, so if you take it there, uh, oh my god, if you take it there, you'll see that it is about here. Yeah, so it's about a little bit below 6,000 Kelvin temperature. So you see that where the sun is. Now that you know where the sun is, now you need to know, like, you need to understand why the luminosity compared to sun of 1. Well, this is pretty obvious. What is luminosity compared to sun? What is this? What does this mean? What does luminosity compared to sun means? Well, luminosity compared to sun means, let me just write this down here. Luminosity compared to sun is equal to, this just means a fraction. Okay, this means a fraction. So if I just add a fraction here, so this just means luminosity of the star divided by luminosity of the sun. Okay, so I make this bigger for you guys to see properly. So this is what luminosity compared to sun means. Okay, this is what it means by what we mean by luminosity compared to sun. Okay, so when I say luminosity compared to sun, this is what I mean. Luminosity of the star divided by luminosity of the sun. Now, when I'm talking about the luminosity of the sun, in that case, the luminosity of the star also becomes the luminosity of the sun. So the numerator and the denominator are the same, so the fraction becomes equal to 1. Therefore, stars that have a luminosity lower than the sun, for them this fraction will be less than 1, that is 10 to the power minus 1 or 10 to the power minus 2, 10 to the power minus 3 and so on. For, for stars that are brighter than the sun, that are much more bright than the sun, for them this luminosity value will be greater than 1. This luminosity compared to sun value will be greater than 1. So it will be like about 10 to the power 1, 10 to the power 2, 10 to the power 3, 10 to the power 4 and so on. So if a star is here, what is this? 10 to the power 1, right? 10 just means 10 to the power 1. So if a star is somewhere here, for example Altair has a luminosity compared to sun of 10. This means Altair is 10 times brighter than the sun. The star Altair is 10 times brighter than the sun. Okay? And then maybe like Aldebaran, about 10 to the power 2 times, about 10 to the power 2. This means 10 to the power 2 is equal to 100. This means Aldebaran is 100 times brighter than the sun. And then if you see Betelgeuse, 10 to the power 4. 10 to the power 4 means 10,000. Okay, so 10 to the power 4 means 10,000. So Betelgeuse is 10,000 times more bright than the sun. On the other hand, if you compare like Proxima Centauri, 10 to the power minus 4. This means this is 10,000 times less bright than the sun. 10 to the power minus 4. Okay, অনেক কিছু বলছি. So far so good. Any questions so far for everything that we have discussed so far? Okay. Something is wrong. Did you guys get lag? I think the connection is all right now, but maybe you got lag in the middle. Okay, we all are. Sir, will you provide the PDF? Sun is a G2 star. Sun minus 5. Sun 5778. Yes. নামাজের ব্রেক দিবা? আসর নামাজ তো আমি পরে শুরু করছি ক্লাস, বাট ইফ ইউ ওয়ান্ট, হ্যাঁ আমি 5 মিনিটের ব্রেক দিতে পারি, সমস্যা নেই. Sun is a G2 star. Altair is from our galaxy. Okay. Sir, M0 and K0 ওই লাইনটা কি রিপ্রেজেন্ট করে? কি জানে আছে? M0 and K0 রিপ্রেজেন্ট করে জাস্ট হচ্ছে ক্লাস M ক্লাসের, M0 মানে হচ্ছে M ক্লাসের হাইয়েস্ট টেম্পারেচার স্টার, K0 মানে K ক্লাসের হাইয়েস্ট টেম্পারেচার স্টার, F0 মানে F plus এর highest temperature star and so on. ঠিক আছে? Remember I told you that the classes are spectral classes are OB, these ones, and then these are again subdivided into smaller groups numbered 0 to 9. So like if our sun is a G2, that means it's like close to 6,000 but less than 6,000. But if a star is maybe G9, then it will be close to 5,200. Okay, it will be like about 5,200 or 5,300 if a star is G8 or G7. Okay, so K0 means 5,200 Kelvin, and you can see that even like if you go here, you can see that K0 is about here, so that will be about 5,000. This is a logarithmic scale, so it's gonna be a little weird for you to visualize, but yeah. So break given. Okay, I'll give a 5 minute break for Asar pair. Starting now. যারা পড়ো না এখন পড়ে আসো। Negative value equal to bright. Yes, negative. The more negative value of absolute magnitude, the more bright the star is. Okay, do you guys have any question? Yeah, Sharier, it's a nice one. যেটা তুমি ইয়াতে দিছো, গ্রুপে দিছো। হ্যাঁ, this one shows even more of the stars. So yeah. আইনস্টাইন ভার্সেস হকিংস, এটা ডিবেট কেন হবে? হকিংস তো আইনস্টাইনের Hawkins is a scientist. Einstein was a scientist. Hawkins stood on the shoulder of Einstein, just like Einstein stood on the shoulder of Newton, just like Newton stood on the shoulder of Galileo, just like Galileo stood on the shoulders of other philosophers and scientists who came before him. Science is not about competing against each other, science is about building on top of each other's knowledge. You stood on the shoulder of me. Like, I haven't, I don't feel I have yet contributed enough to the scientific community that you can stand on my shoulder, but like, yeah, I'm trying to give some input to the scientific community. Okay, আমরা start করি. The break is over. Let's resume from where we left off. All right. So far, everything that we have discussed, Hertzsprung Russell diagram, we have discussed the axis only. We haven't gotten into the diagram itself. So we have discussed the two axes, the x-axis and the y-axis. On the y-axis, there can be either absolute magnitude or luminosity compared to sun. Luminosity compared to sun, 1 means it's the luminosity of the sun. Greater than 1 means more bright than the sun. Less than 1 means less bright than the sun. Absolute magnitude, the higher the values, that is the more negative the values, the more bright the star, the more positive the values, the less bright the star. So overall we can conclude from this diagram, and the x-axis is effective temperature or spectral class or color. So in the x-axis, it is from left to right, temperature increases. Okay, so overall we can conclude two things about the Hertzsprung-Russell diagram, that is, from left to right the temperature of the star increases, and from bottom to top the brightness of the star increases. Are these points clear? Okay, I hope these are clear. If these are clear, now tell me, let me just pull this up. Yeah, okay, so tell me this: if a star if a star is if a star is bright and hot, like very bright and very hot, where will it be in the HR diagram? What is your answer? Let me know in the comments, or just think of the answer. If a star is very bright and very hot, where will it be in the Hertzsprung-Russell diagram? Ha ha ha. Takes help from their legends. Yes, every scientist takes help from their legends, definitely. Okay, now answer me this. If a star is very bright and very hot, where will it be in the Hertzsprung-Russell diagram? Well, it's very bright, so it will be very at the near the top, and it's very hot, so it will be to the left. So the answer is left top corner. Get it? If a star is very bright and very hot, it will be on the left top corner. Okay, both of you said left side and blue area. Left side and blue area, fine. Left side, blue area, but where? Bottom or top? It will be at the top because it is bright. Very bright, so top. Very hot, so left. So left top. Now, what if I repeat the question, but this time I ask you, let me remove the answer. This time I ask you, like still very hot, but very dim and very hot. What will be your answer? So it's like not so bright, okay, not so bright, but also, but it is at a very high temperature. So this will be no, not right up. No, it's still hot, high temperature. So it will be to the left, but it is dim, so low brightness. So brightness is on the y-axis, so it will be near the bottom. So it will be left bottom corner. Clear? So it will be left bottom corner, not right. Left side down. Yes, that's the answer. Left side down. Clear? Okay. Now, what if, let me keep asking more. I know it's getting easier for you now. Now, what if I ask you the same question again, but this time I ask, let's say, very dim and cold. Very dim and cold. Where will that be? So it's dim, so low brightness, and it's cold. No, not middle top. Why will it be middle top? It's cold, so it's very cold. By cold, I mean very cold. Okay, so like it will be to the right. Since it's very cold, it will be to the right, and it's very dim, so it will be bottom. So this will be right bottom corner. And we have only one case left. What is that? If a star is very bright but very cold, or like, okay, very bright and very cold, so what will that be? Very bright, so it's gonna be top, but very cold, so it's gonna be to the right, so this will be right top corner. Understood? So very bright and very cold, it will be right top corner. Okay, so let me just number these. Let's say this is quick. This was one. Oh, okay, I can just, I guess, go right. Oh wow, sorry for the bad noise. মশার ওষুধ দিচ্ছে. It's crazy. Oh, yeah, sorry about that. We have dealt with the noise. Alright, now back to our topic. Like I was saying, so um, so that's question one. Let me just make this a little bit nicer so that you guys can easily read it later. Okay, I hope this makes sense. Alright, this makes sense? Cool. If this makes sense, let's just go back to the Hertzsprung Russel diagram. Okay, so the axes are clear, the positions of the stars are kind of, we have an idea where a star will be and all that. Now we need to know a little bit more about brightness and temperature. to determine a, a little bit more, to get more information. The first thing that I'm gonna say, this is, we are still talking about the HR diagram. Okay, so the first thing I'm gonna say is, the greater the size of a star. Did I tell you this before? I feel like I've told you this before. No, no. Okay, no problem. I didn't tell you this before. That's all right. So the greater the size of a star, let me just let me just get that real quick. Um, yeah, the greater the size, okay, the greater the brightness, okay. And now the smaller the size, oh wow, sorry, and the smaller the size, obviously the less the brightness, okay. The smaller the size, the lower the brightness, okay. Another thing is, the smaller the size, the higher the, or rather I'll just say it like this, um, high temperature, um, high temperature usually means, not always, this is not always, usually means, there is no question 6, there are only 4 questions, 1 2 3 4, there were just 4 questions. Do you have any other questions so far? No. The higher the high temperature usually means, not always, usually means small size. Um, usually means small size, and also vice versa. Like low temperature usually means big size. Oh wow, that was unexpected. Low temperature usually means big size. Okay, is that clear? Is that clear to everyone? Okay, now you may have a question, the best question that you can ask, why? Oh, about the updated PDF, before this class, I updated both PDFs. Please download them from the group again. But after this class, I'll again update the two PDFs. Okay, after this class, I'll again update the two PDFs, because of course we're covering more stuff here. Okay, so the larger the size, the greater the brightness. The smaller the size, the lower the brightness. The larger the temperature usually means smaller the size, and low temperature usually means large size. The question is why? Now, you see, the bigger the size, the greater the brightness is pretty obvious. The bigger a star, um, the more visible it is. Okay, or rather, if I want to tell you a little bit more, the bigger a size, the greater the size, like big size means big surface area emitting radiation, which means, so more radiation emitted per second, so greater luminosity, so greater brightness. All right, big size means, like, let me use some better words, like large size means big is such a ambiguous word. Large size means large surface area emitting radiation. So more radiation is emitted per second. So greater luminosity. So greater brightness. Okay. So simply speaking, if you have a bigger light, if you have a big lamp, it will be more bright. If you have a small lamp, it will be less bright. Pretty obvious. Okay. Why high temperature usually means small size? This is not always the case, but this usually means small size. Why? Well, small stars are greater than massive stars are cooler than the sun. Yes, massive stars are not all massive stars. Like not all, not all. No, 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 not all. Let me. I'll clarify that. High temperature usually means small size. Usually, this is not always the case, but usually, this is the case, especially for white dwarfs. All right, let me just give you an example. For example, white dwarfs. White dwarfs are small, right? But they have the same. They have the similar amount of energy as the red giant from which they form, right? Because they white dwarfs form from a red giant, right? So the red giant had a lot of energy, and now the white dwarf is basically all of that energy in a very small space. So large amount of energy in small space means higher temperature. Do you understand my explanation? White dwarfs are small, but they have the similar amount of energy as the red giant from which they form, right? So large amount of energy in a very small space means higher temperature. I hope this explains it. Alright? What about the opposite case? High temperature. Why does high temperature usually mean large size? Well, for example, red giants and red supergiants have enormous amount, have like let's just say have a lot of energy, right? Red giants and red supergiants, these have a lot of energy, but, or I'll say like, oh damn it, what happened? However, this energy is distributed over a large space, right? Just the opposite of white dwarf. In white dwarf, all of the energy is like focused in a very small space. But in red giants or red supergiants, there's a lot of energy, but that energy is distributed over a large space. So it means lower temperature. And that is why they are red. You understand my explanation? But also, this is not always the case. Temperature and size are not always directly related, because temperature also depends on the fusion reactions. Okay, yes, you can write this as a separate point, no problem. But temperature and size are usually related like this, but not always. Okay, these are my explanations, the bracket ones. Okay, and these are the facts. Okay, these are just your facts. So, like, these are very important. These are your facts. This is also fact, but again, usually is a key word here. Notice that it usually means it's not always. Okay, so these are important, and those are just my explanation for you guys. Let me just convert everything to times New Roman so that it looks nicer. Yeah. Okay, now that we have gotten that out of the way, you don't have to. It will be on the PDF. You don't have to write all of this down with me. Although I'm typing it out as I speak, so you should be also able to write it out as you hear. But it's okay if you can't write it out. They will be on the, they will be on your updated PDF. No worries. Okay, so we have learned a lot of things, right? Now let us try to analyze the Hertzsprung-Russell diagram. This is the Hertzsprung-Russell diagram, right? Again, even this one is a little bit more complicated. So we will switch to a very simple version. A very simple, clean version. Okay, so we just have like color and luminosity. That's it. I'm thinking of, I'm getting rid of everything else for a second. Just think of color and luminosity. Again, remember, the x-axis label and the y-axis label can change. If you see these values as your y-axis, you will say this is luminosity compared to sun. 10 to the power minus 4, 1, 10 to the power 6, 10 to the power 5, so on. But if you see these values on your axis, y-axis, 14 and above you have like minus 10, okay, or like you have a 0 in between, then this is an absolute magnitude. It's a different y-axis label. So in exam you may have to label the axis. So be careful when labeling the axis. Look at the values, which values are given. What was your question, Sharia? Explain my one. I want to know about it. What was your question again? Why this happens? I explained why this happens, but I'm not sure what's your other question. Okay. Also, now if you look at the Hertzsprung-Russell diagram, the simpler version, here again the x-axis label may also change. There can be three labels for the x-axis. It can be temperature, it can be spectral class, and it can be color. For example, in this case, the x-axis label will be simply color, and it can even instead of this, it can be like this. The label can be something like this. It can be like um, the label can be. Oh, okay, let me just show you this. Um, you see, the label may even be like this: blue, white, green, yellow, green. Like let me give another tab. Yellow, orange, red. It can be like this. It's not necessarily that it will always be a gradient color like this. Especially in your exam paper. Your exam paper is not going to be colored. Remember, your exam paper will also always be um, black and white, right? So there will be labels like this: blue, white, green, yellow. So in that case, the x-axis label is color. But if these are temperature values, then the x-axis label will be temperature. If these are O, B, A, F, G, K, M, then the x-axis label will be spectral class. Okay, I will repeat what I said about the y-axis. No, you won't have to draw it in the exam, but you have to know it very well, and you may even have to draw it. Like you have to know this diagram very well, okay? Because they will ask you to label, they will ask you to put the values, they will ask you to draw the main sequence, they will ask you to show where the white dwarfs are, where the red giants are, where the supergiants are, etc. That is why I'm taking a whole class on just this diagram. It's very important for the exam. Okay. Now let's go to this. Okay, so blue, white. Yeah, okay, let me repeat the y-axis. On the y-axis you can either have absolute magnitude. If you see that the values in the exam are 14, 12, 10, 8, 6, 0, then the label will be absolute magnitude. But if the values are like this: 10 to the power minus 4, 1, 10 to the power 5, then the label of the y-axis will be luminosity compared to sun. So you have to understand, you have to decide the y-axis label depending on the y-axis values. Also, if in you may be given in your exam the y-axis label and you have to put in the values. So if absolute magnitude is given, you need to write 14, 0, minus 10. But if luminosity compared to sun is given, you need to write 10 to the power minus 4, 1, 10 to the power 5, like that. Got it? So it's very different. So you need to remember this. Now, last thing. This is the last thing. So you can see in the diagram that there are some, like even in the more complicated diagram, you can see some patterns. Even in the original diagram, you can see some patterns. Even in the picture that Shahryar sent in Messenger, if I can get it open here, but like you can see that there are some clusters. This is one group, this is another group, this is another group, and this is another group. So there are some like groups of stars, right? And these groups are basically different, like let me just get that diagram too. It's a really nice diagram. Okay. Yeah. Okay. You see, much more complicated, lot of more stars, but ultimately the idea is the same. You can see the spectral class here. You can see the temperature here. You can see luminosity compared to sun. You can see absolute magnitude, and you can see several groups. You can see like white dwarfs here, the main sequence group here. You can see the the giants here, and the supergiants here, and you can see some more stars around here. I'll explain what they are in a second. So overall, to summarize, the diagram looks like this. Very simplified. This is very simplified, right? Some white dwarfs here, the main sequence here, the giants are here, and the supergiants are here. Now, why are the white dwarfs here? No, the Hertzsprung diagram only have two axes, x and y, x and y, but the x-axis can have three values. It can be color or temperature or spectral class. The y-axis can have two values. It can be either absolute magnitude or luminosity. It's not a four-dimensional graph. It's not a three-dimensional graph. It's a simple two-dimensional graph, but it's a diagram because it's a logarithmic scale, and also the left is positive in the x-axis. So basically, the values can change. Anyway, now moving on. So the different groups I was talking about. So first of all, try to think about this. Why are white dwarfs here? Why are the white dwarfs here? Well, remember, white dwarfs are small, right? White dwarfs have a small size, so they must have a low brightness, correct? Small size, so low brightness. So low brightness, that is why they're near the bottom. They are near the bottom, so low brightness. Also, small size, but white dwarfs have very high temperature. That is why they are white. They are white, correct? They are white. As they are white, so the white dwarfs must be very high temperature. So they will be around here, blue white, in the blue white region. Okay, this is kind of weird, but you can see here, like white, in the blue white region. White dwarfs will be in the blue white region. Okay, so white dwarfs will be in the mostly white and blue region. Okay, so high temperature but small size. Now think about the giants. The giants. The giants are red giant usually, right? Most giants that we know about are red giants. So they will be above the red. They will be exactly above red. And they are large, right? They are giants. They are large. So the sun is around here, remember? Sun is around here, like one here, the sun. So the giants are definitely bigger than the sun. As they are bigger than the sun, they will definitely be more bright than the sun, because the greater the size, big size means large brightness, right? So the giants will be up there. The giants will be in the upper part of the diagram, and they will be to the right. They will be to the right because, well, they are giants, correct? And if you think about the super giants, they are even bigger, but as they are even bigger, they also have low temperature. So red super giant will also be on the right, but it will be on the very top. So the supergiant, the red supergiant, will be at the very top. Now I've talked about supergiants, I've talked about giants, I've talked about white dwarfs. What about the main sequence? Well, in the main sequence, so this is the main sequence. You see the main sequence? Okay. Which stars are in the main sequence? All stars in their stable state are in the main sequence. All stars that are in their stable state are in the main sequence, right? So, yeah, you don't need to give dots. You need to like draw the shape where the main sequence is. So the main sequence is around here. You need to draw this shape. You need to draw this shape of the white dwarf. You need to draw this shape of the giants, and you need to draw this shape of the supergiants. I'm showing you this diagram for understanding, this diagram for understanding, this diagram for understanding. But for the exam, you need to perfectly remember this diagram, and this one is from your book. This one is from your book. So when you draw the diagram in the exam, you just show the shape like around here. Show the region where the white dwarfs can be found. You cannot pinpoint Poicon B or Sirius B. You cannot do that. You don't need to remember that. But you need to show the area. The white dwarfs will be here. The main sequence will be here. The giants will be here, and the super giants will be there. Okay. Now understand this, that the main sequence, which stars are in the main sequence? All stars in their stable steady state are in the main sequence, right? In their steady state, all stars are in the main sequence. So then why is the main sequence so big? Like in the main sequence you have low brightness stars, but you also have high brightness stars, and you also have the sun and similar stars. Well, obviously there are massive stars and there are low mass stars. Remember, main sequence, you have the average star like the sun, and you also have the massive big stars. So the massive big stars are around the top of the main sequence. So the massive big stars will be found here, near here. Like Achernar is a massive star. Regulus is kind of bigger, much bigger than the sun. But like Proxima Centauri, Barnard star, these are very small stars. Even the protostars can be found here. The protostars. Giants and supergiants, low temperature, and white dwarfs, high temperature. Yes, correct. Buffering. Um, okay, the connection is back. All right. Um, okay. Repeat what? Which part? I'm not sure. Um, you can watch it. You can watch back the video later, please. Okay. So to sum it up, the white dwarfs are here, the main sequence is here, the giants are here, super giants are here, and you remember the axis. To sum up the main sequence part, the large stars, the massive stars in the main sequence will be near the top, and the small stars in the main sequence will be near the bottom. Like the protostars will be here, the supermassive stars will be there, and the sun-like stars will be near the sun. So like these yellow ones are sun-like stars, these blue ones are massive stars, and these red ones are protostars. You can look at this diagram, the complicated one, and you will see that like Regulus is near a is one of the massive stars, supermassive stars. Okay, and then like there will be protostars kind of around here. Okay, like there will be protostars like around here. If you look at the Wikipedia diagram, you will see like these are small stars. Okay, and like those are large stars. you can see there like 30, you see 10 solar mass, 30 solar mass, 60 solar mass. So the massive stars are like around the top. Oh, do we not need to, we just give random dots? No, we just give the shape. Yes, mine already answered, good. So we just give the shape, like we just draw this shape, like the main sequence stars will be around here, the white dwarf stars will be around here, giants will be around here, supergiants will be around here. And that is all about the Hertzsprung-Russell diagram. Hope you liked it and hope you enjoyed this topic. I think the Hertzsprung-Russell diagram is a really fun diagram. It shows all the stars and their classifications. If you have any questions, ask me now and then I will end the class here. Any questions from Hertzsprung-Russell diagram? What is your question? Protostar koi thakbe? Protostar will be around the bottom right. Protostars are what? Very small, so they will be near the bottom, and they have low temperature because they are not a big star yet. So they have low temperature, so they will be to the right. So protostars will be here, bottom right. Room tour? No, thank you. Protostars will be around the bottom right. Any more questions? Okay, if you don't have any questions, I'll make one quick summary and wrap it up. The Hertzsprung-Russell diagram has, it's a plot of all the stars that have been discovered so far. The axes are logarithmic, so they don't increase like a normal graph, they increase rapidly, like 4000, 4, 6, 7, 10, 30, okay, and then 14 to minus 10. The x-axis values increase in the left direction, so that's also weird from a graph. On the left direction, you have increasing temperature. Oh, excellent question, Sharyar. If we are said to identify an unknown star, what will we do? Unknown star. Let's say a star is given in the Hertzsprung diagram here. Let's say the exam, in the exam you are given a star here. Oh my god. Okay, a star is given here, and you are asked, well, in what stage of its life cycle is this star? What will be your answer? What stage of its life cycle is this star? Well, you will obviously answer it's a supergiant. It's a supergiant because it's a very high brightness star, a very low temperature star. So it's very huge, but it has a low temperature, so it's red. So it's a red supergiant. So okay, so it's a red supergiant. So in which life cycle is it? Then this has definitely come from a supermassive star, because only massive stars much larger than the sun, only they will become a supergiant and eventually become supernova. And if you're asked what will this star become, well, you will say this star will undergo a supernova, and then it will become either a neutron star or a black hole. Similarly, if you're given a star here, you will be able to say that this star is like what? This star is a white dwarf. If you're given a star here, you will say it's a massive star. If you're given a star here, you will say it's a sun-like star, average star. HR diagram বলো না, ভালো না. Oh, stable star maintains law others don't according to the graph. No, what law are you talking about? All laws are being followed. Lag, massive. Lag again. Sorry. The internet has started to fall off a little bit once in a while. Anyway, but our topic is over, so like if this gets fixed, we will end the class here. Okay, yeah, the connection is all right, and let me end it here. Repeat it once more, please. Oh, okay. If we have an unknown star, well, if we have an unknown star, if it is around, if it is near Sirius B, then it will be like if it is near here, then it will be a white dwarf. And you will say it has a high temperature and it is a low brightness, so it's a small star with a very small size but a high temperature. If it is around here, you will say it's a large star, huge star, it's a supergiant, high low temperature, high brightness, large star. If it is around here, you will say it's a low temperature, high brightness, so it's a red giant. If it is near here, you will say it has a luminosity close to the sun, so it's a sun-like star. So it's an average small size star. If it is around here, you will say it has a very high temperature and it's a very high brightness star. Very high temperature, very high brightness star. So you will say that it's a supermassive star. Like it's a massive star. It's a star with a much larger mass than the sun. And if it is around here, you will say it's a very small star, smaller than the sun, and so on. High temperature and small size. So to draw an unknown star in an AJ diagram, we need to look at the features of, yes, we need to look at the features of uh, temperature and brightness. Temperature, brightness, size. Black hole or neutron star, well, they are not usually included in the Hertzsprung-Russel diagram. Black holes are definitely not included because they are not actually stars. And neutron star in HR diagram will be, let me check this real quick in Google. Well, yeah, a neutron star is not usually included in the Hertzsprung-Russel diagram because let me just show you a picture real quick. Because like if this is the Hertzsprung-Russel diagram, the neutron star will be like here, way outside the. If this is the Hertzsprung-Russel diagram, the neutron star will be like here. It will be like it's like much higher temperature than any other star, but also a quite high brightness. So it's like white dwarf, but way more temperature. Okay, so neutron star will be like is not included in the Hertzsprung-Russel diagram. The Hertzsprung-Russel diagram is only for normal stars and white dwarfs. Okay. Oh, by the way, a white dwarf will eventually go from here to here to here to ultimately cold black dwarf. So white dwarf actually loses temperature and loses luminosity, so it slowly goes from here all the way to the bottom. Okay, a neutron star and black hole, they are not included in the H diagram. Clear? A spiral galaxy is a galaxy that has the shape of a spiral. For example, the Milky Way. This is totally out of the box question. So I think you don't have any more questions from Hertzsprung-Russel diagram, right? Because its temperature is much higher and much bright. Yes, it is kind of bright. It's not as bright as large stars, but its temperature is much higher. Okay, let's wrap it up here. Thank you for your questions. Thank you for attending the lecture. I'll see you in the next lecture. Thank you. Allah Hafiz.